All right, hello everyone, and welcome to the first talk of the Hot Electric Seminar Talks in fall 2025, as John has recently renamed the series. So today we have Jon Sterling from Cambridge, who will ask, is it time for a new proof assistant? Take it away.
Well, thanks, Carlo. Thanks for inviting me also. It's great to see so many familiar faces in the room. So good to see you all. I apologize in advance for how wordy my slides are. There's a lot of people who don't have time to show up or to watch 20 minutes of YouTube ads, and so I wanted them to be able to download the PDF and see what I said. So that's how that's going to be. Um, so yeah, I'm asking the question: is it time for a new proof assistant? Um, and just to take stock of where we're currently at in the world of dependent type theory, and I want to note that dependent type theory isn't everything in the world of proof assistants, but it's mostly what I'll be talking about today. Um, so we have a lot of really interesting projects. Lean has been getting the most press lately. It's a fantastic proof assistant for classical mathematics, and it has a great mathlib library. It's getting better every single day due to the massive investment in tooling and quality of life by the Lean Focus Research Organization. So shout out to that team for the amazing work that they're doing, and shout out to whoever's funding them. For making it possible for that to happen. Um, Agda continues to be a great proving ground for interesting experimental type theories, like cubical type theory, as well as standard type theory. And we've got a number of interesting libraries for mathematics in HoTT in Agda. A couple of them are Agda UniMath type topology, the One Lab, and the cubical library. And I'm sure there's other libraries that I'm not mentioning here, and I don't mean to slight the authors of those libraries. Well, there's rock, of course, and well, they've got a lot of stuff going on. There's at least a couple strong libraries in homotopy type theory, and there's a lot of activity on the computer science side of things in rock. Um, and then we have this whole range of highly experimental systems. So Idris 2, they're experimenting with quantitative type theory. Recently, Mike Schulman and his collaborators have been who was involved in that? Elif Eskuplu and a few others. They've been developing Narya, which is a proof assistant for higher observational type theory. And I recently found out about another one called Istari, which is a proof assistant for some predicative version of computational type theory. Seems to do a better job than I ever did when I tried to do such things. Um, so in any case, in the world of HOTUF, however, most of our energy is invested in Agda and Rock at the moment. So there's the cubical world, and then there's the orthodox world. The cubical people are developing interesting and innovative approaches for doing homotopical mathematics. And then there's some of us who prefer just to work in the language of Bookhot, and that's represented in a number of libraries that I've mentioned here. The thing is that although we've been very active in our community, except for a few years of interest, we haven't really attracted that many mainstream mathematicians to stay with us. And it's not a popularity contest. It's not a popularity contest, but part of the goal of what we're doing is to make mathematics better and to help people who want to learn and do mathematics. And so I do think we need to take seriously where the energy is being focused. You know, um, hype cycles are a thing. You live by the hype cycle, you die by the hype cycle. If we look at what happened, there was a lot of interest initially when Vladimir Voevodsky promoted homotopy type theory and univalent foundations, this invention of his and others in the community. Um, I think a lot of the interest among mainstream mathematicians was simply because Vladimir Voevodsky was a famous mathematician, a Fields medalist, and a mathematician of the first rate. Um, and although I don't think that he intended to give this impression, I do think that many people got the impression at the time that hot UF was the only way forward. And when that turned out to be obviously not the case, there was a bit of a backlash. And just in time for that backlash, we've had some figures who have been able to stir up interest in formalization through other approaches, in particular, an orthodox classical approach represented in the lean system. Um, I think that there were a lot of fair critiques made by this crowd. But on the other hand, I also think that there was some kind of misinformed statements which may have given people the erroneous impression that univalent foundations is somehow incompatible with classical mathematics, when in reality it's very compatible with classical mathematics, as much of the work of the people in this room has shown. Um, we're on another hype cycle now. If you take tea too often in the Royal Society, or you spend too much time in policy circles, as one is apt to do when having reached certain heights in one's career, um, the only thing anyone wants to talk about with you is AI. And so you start spreading AI hype and so on. And I guess a question for our community is whether or not we need to bend the knee or if we actually have something to offer today. Um, and I think we do. That is, I think we have something to offer. Um, I wanna be really honest about something. The hype cycle is one thing, but there's real non-hype reasons why lean is so popular, and I'll tell you a couple of them. One of them is that I'm not kidding about this. This is for real. You can try it. You can get lean installed and running in less than 5 seconds. It doesn't matter what operating system you have. You open up Visual Studio Code with a lean file in there, and it will just download what it needs and it will work. I'm not joking. If that were the only thing that Lean did, it would make me choose it if I were trying to teach a course or something at the university. Lean has great editor support out of the box. You don't need to use an archaic editor. I love Emacs, don't get me wrong, I love it, but the kids don't love it. Um, and the type classes and things like that work pretty well. You can pretty much get to work and it's okay. Um, you don't have to mess around with many different, very subtle approaches that all have problems that cause them to break down at some point or another or force you to formalize your stuff in some obscure and strange way. It's pretty much okay. It's not perfect, but it's pretty much okay. And then the real elephant in the room is the MathLib library, which is a fantastic, enormous library that has a lot of mathematics in it and a lot of energy behind it. Um, and then finally, one that's really near and dear to my heart is that if lean ends up proving false one day, they're going to fix it. It's a priority. Um, you know, I don't mean to pick on Agda. Agda is great, and I use Agda for all my research. But Agda often proves false, and it's not always considered a bug that should be fixed. Oftentimes, there's features that we're not allowed to remove from Agda, and those features are inconsistent. That's a cultural matter, I think. So I also think, I want to just, be honest here and give some credit where it's due. Kevin Buzzard made a point at one time that people in our community have been focusing a lot on problems of logic rather than problems of mathematics. And well, there's some truth to that, although many of us in this room have been doing both. Some of us have been doing mainly mathematics and not logic at all. Um, I've been doing logic, I'll cop to that. But I would say that logic and mathematics, you shouldn't view them as opposed in a bad way. They're two parts of the same dialectic process. But mathematics is the leading aspect, and logic is the trailing aspect. So if you think about it as a dog and its tail, which one is doing the wagging? I think is the question that is worth asking every once in a while. Um, So we've spent a decade doing cubical type theory, for example. And this has been a lot of fun. I've learned a lot in the process. Many members of the community have contributed great results to the study of cubical type theory. Computer scientists, we got interested in it because it was a hard problem about computation. How do you make hot compute? Um, and as a community, we solved that problem. The thing is, though, that to do mathematics, if you want a proof assistant for doing mathematics, you don't need it to compute. And in fact, we pretty much want to stop it from computing a lot of times because the computation will cause the goals to get too complicated and too unreadable. And even the times when we really do want it to compute, like you want univalence applied to some equivalence to actually call the function that is underlying the equivalence, in cubical type theory, this is going to leave behind some dead coercions. This is even in that case, the computation is not doing exactly what you want. So you still have to reason with some transports. Um, Cubical Agda has been a fantastic project. We've definitely learned a lot, and great libraries have been built. The Cubical library and the One Lab. I especially love the One Lab. But it uses De Morgan cubes, and so, well, there's some people in the room who could say with more authority than myself as to whether this is the case. That's why I put a question mark here. But it seems to me that it might not be sound for standard mathematics, or if it is, it would be for some very complicated reason. Um, that's a little bit of a concern for me as far as the use of cubical agda for formalizing mathematics. Um, and even if we did switch to a system that was clearly sound for standard mathematics, for instance, one based on Cartesian cubes. I'm starting to think that the cubical type theory has some usability issues that, I spent years trying to solve these issues, and I do hope that members of the community will continue to work on it, but I am a little bit worried that these issues are harder than we thought. And that we may never have a system that has reliable, complete unification for a reasonable pattern fragment. So that seems like a real problem for us to solve, or a problem for us to stop banging our heads against. Um, Maybe from my perspective, after all these years, the thing that has staying power is the cubical models. That thing seems to be the most important result here in terms of its implications for mathematics and its implications for proof assistance, because you can have a cubical model of book hot that may justify equations that we want, and more equations than hold in book hot, and yet still be interpretable into the infinity tuples of spaces. So that seems like it's a pretty good thing. Um, so I also want to talk about UniMath. This is one of the things that I think has been the most beautiful in the past 2 decades to come out of our community. Actually, it was, I think, a talk in Wuhan, I think that's where it was, that Voevodsky in 2003 called for a computerized Voevodsky project. He was tracing this progression from paper mathematics to hypertext mathematics to computer verified mathematics. It's a vision that took him many years to figure out in what modality he wanted to solve it. But in 2014, he introduced the UniMath project as a unified library of general mathematics, not just some specific kind of mathematics, but any kind of mathematics belongs in there, but from the point of view of his univalent foundations. And then a few years back, Agda created this beautiful Agda UniMath library, and it's been really wonderful to watch so many young people getting involved in it and actually having coding in UniMath be their first experience of homotopy type theory and univalent foundations. So that has been a really amazing thing to watch. But if there is a Voevodsky project happening right now, I'm afraid that it's not UniMath, it's MathLib. So I think it's worth asking, why hasn't this really taken off too much outside of our community? And there could be a lot of reasons. I don't want to blame it all on outside factors, although those could play a role. But if I had to focus on some inside factors, maybe the style of formalization that has to be used in there is a bit too low level and It's lots of plumbing. You can see the plumbing coming out of the walls and the ceiling. And, Voevodsky had some good reasons for designing it this way and imposing those constraints. In part because the existing proof assistants have a bunch of features that are kind of dubious. And rather than trying to figure out exactly which parts of those are okay and which ones are likely to be portable to future systems, he said, no, let's just do the minimal thing and avoid all of that stuff. My perspective here is that if we want to actually address the underlying problems that Voevodsky noted, um, I think we have to take seriously a return to foundational orthodoxy, and I'll say a bit more about what I mean by that. But we should do so in a way that doesn't sacrifice usability. And I think as a community, we're well placed to do both at the same time. Um, I still believe in HotUF. But the thing is, I can't tolerate, I just can't be doing the hair shirt anymore. So I need reliable and flexible tools for algebraic hierarchies. I need reliable control over when the definitions unfold, how things get displayed as goals. I, life is too short. I need to be able to use this to teach my undergraduates. I'm serious about this too. I really actually want to use it to teach undergraduates and not teach them hot. I want to use it to teach them mathematics. Um, so for this, okay, on day one, I need easy installation, editor support. I need to minimize weird type theory things that we have to explain away, things that are just encoding artifacts. And another thing that's important, I'll talk about it more. I need the code to actually contain a history of the deductions that were made, because this is people read code to understand it. And if you look at like some Agda code with a bunch of pattern matching, like matching on ruffle, ruffle, ruffle. You can't tell in what order that was done, and you can't figure out how the person who proved it in the first place ever got there. So I need something that actually records the history of ideas. And I need to be able to communicate with normal mathematicians, which means that I need the thing to be clearly sound for standard mathematics. So I can't be doing any kind of weird De Morgan cube. I can't be doing this. I'm sorry. Um, so after considering all of those factors, I figured out that what I actually needed was there all along, at least in terms of the type theory. I really just need book hot. But I need a proof assistant that is uh, a lot more user-friendly than what we have right now. Um, and we could build on Lean, and there could be ways to do that. And I think that some members of the community are exploring how we might do that. I'm interested also in developing a bit of independence from Lean, even if it's costly, uh, because I'm still wary of the experience of Lean 2, which I don't blame the Lean people for getting rid of hot in Lean 2 after Lean 2. I don't blame them at all, but we have to walk on our own 2 feet sometimes. So I'm open to a variety of approaches, and I hope that people will pursue many avenues. So the elephant in the room, of course, is if we're talking about a new proof assistant, why not use higher observational type theory, which is one of the most interesting things to emerge in the past few years. Um, I think it's really, really cool, and I'm super interested in it. But I also think that at least at this time, it's not quite what I'm looking for. So one thing is that I've been fully converted to the J rule, path induction. I was doing cubical type theory on my PhD, but then I realized how important J is and how important it is that it compute on REFL. Um, and we don't really have a good way to do this in cubical type theory. Semantically, it's okay, but syntactically, there are problems. So the same thing, by the way, happens in higher OTT. As far as I'm aware, the J rule isn't going to compute there. Another cool aspect of higher OTT is that each type is defined together with all of its identification types and some kind of a co-inductive hierarchy. So that's cool. And so you get some kind of structure identity principles up to a definitional isomorphism, which I think is very interesting. Uh, maybe it's up to at least a definitional retraction. I'm sorry if I'm getting something wrong. I apologize. The thing, though, is that the way the system is organized, these are not exactly the SIPs that you expect for when you write down an algebraic structure. So I think you'd still probably want to characterize the path spaces. We can already do that in HoTT. That's where I'm at there. And I was really excited, but then I started getting bogged down as soon as I started figuring out how all the symmetries work in there. And anyway, I think it's all fine and good, but it's getting about to be as complicated as cubical type theory, and I honestly wanted something simpler. So anyway, I need something that is simple because I want to implement it with state-of-the-art algorithms and things that we know how to do. And I'm totally open to revisiting this question in the future. And I expect to continue following higher OTT with great interest. But for now, I think book hot is actually what I need. Um, this is a cool picture. Um, we always have to have a bird name in our community. Um, uh, there, there's, there's Rock, which I think is some kind of a legendary bird. This has renamed a different name that was also referring to a less legendary bird. And Agda also is the name of a hen in a bawdy Swedish song. I wanted something orthodox, so the oldest kind of bird. Um, so I chose the pterodactyl. So here's my goals. I want it to be delightful for me and for my students. I want it to be predictable for someone who is educated about how it works. I want it to be efficiently implementable. I want it to be orthodox in its foundational assumptions. And I want it to be compatible with HotUF from the start, not just merely compatible, but with a lot of stuff built in. Um, and an obvious consequence of these assumptions is that it would be equally usable for constructive and classical mathematics. So major design constraint, at least for now, unless something like HoTT emerges as something that would fit my requirements. Whatever the system is, it needs to be interpretable in a conservative extension of book hot. It doesn't have to be literally book hot, but it needs to be something that book hot can embed into. And it's okay if the image of the interpretation satisfies more judgmental equalities. I just don't want it to satisfy less, because then it wouldn't be an interpretation after all, would it? So I think we have an opportunity here, and I'd like to explore the possibilities. So let me talk a little bit about some of the problems I'd like to solve. So the first one, algebraic hierarchies. Nothing is more frustrating, is it? We have type classes in many systems like Rock. We have instance arguments in Agda. I think that's what they call them. The way we usually set it up is that we will quantify over a type and then we'll impose some structure on it. So the thing is, though, that I don't know if you can see I've highlighted something. When I mention the type later on, it's just a type. We've forgotten what structure it had. Maybe it has many different structures. And then the type class database kicks in and tries to figure out what structure we were talking about. It's actually pretty easy in this case because G is a variable, but in general, this is the kind of problem that is really a difficult kind of problem to solve. In order to solve this kind of problem reliably, you need higher order unification. So there is something called Miller's pattern fragment, which is a higher order unification problem in general is undecidable, but there's a fragment of the unification problem that is both well-defined and decidable, and exactly 0 proof assistants implement this fragment. I'm not kidding. That's a bit of a disappointment. So the result is that anything that relies on unification in Rock, in Agda, in Lean is actually highly unreliable and highly unpredictable. So that's not where I want to be. The thing is that in like real math, when we're writing, on paper, or on a blackboard, or in a text document, we just say let G be a group. G is a group. It's not a type that happens to be the carrier of some undisclosed group. And by the way, it could be the there could be more than one group structure that we're interested in with the same carrier. So this approach of saying let G be a set, which by the way happens to be the carrier of a group, and let F be a binary function on G, and oh, it happens to be the multiplication operation of that group. This is not how mathematics works. So I like the former. The former is called bundling, and actually a lot of systems will use this method. So there's a great library called MathComp, which is used as part of the solution to the proof of the four-color theorem in ROC, and they bundle everything. Now they do it in a way that poses some challenges. Of course, if you bundle everything, you still need to unbundle sometimes if you want to talk about, say, two groups that share the same carrier set. Okay, so you need some way to deal with unbundling. They do it using something called mix-ins. All right, fair enough. But they still try to actually hang the identity of that group on just the type. So they have the type, and then they try to use the unifier to find the group that it came from. So this is an approach that's used in MathComp. It was also used in the Matita proof assistant in the context of what they called unification hints. So this is a bit difficult to wire up, but there's an experimental tool called Hierarchy Builder, which will basically generate all the code using logic programming. And this is pretty cool. I tried it a few times and I like the idea, but I kept getting into trouble and receiving error messages I didn't know how to interpret. I think it shows promise, but I'm going to do a different approach. Zooming out a bit, in everyday mathematics, we don't have this whole ceremony about saying, let G be a group and let E be a group that has the same carrier as G. We can just say that and it's okay. There's no problem there. It just works. And I think that we should be able to bundle and unbundle freely any number of fields in the algebraic structure without needing some laborious conversion function or any kind of strange thing to recover the bundled version from the unbundled one with the unification hint. I think we should just support it directly. The other lesson, I think, is that it's of highly questionable value to deduce algebraic operations from a type, because the type could carry many structures. So it's completely impossible. If you asked a mathematician whether we should do this, they would have said no. So we shouldn't do it. And then finally, I have many conversations these days with Larry Paulson, and he's been telling me all about what they've done in Isabelle over the years, and it seems that in Isabelle they actually have a very elegant and simple solution to this problem called locales. Not our kind of locales. Locales for them is something like a module or a type class or a section, but none of the above and all of the above at the same time. And they work great. So I think that we should take some of those ideas and adapt them to dependent type theory. If you want to make a programming language, you should first write the code that is going to be writable in that language, even if you don't know how to implement it. This is a good way to think through the ideas and see if it's viable and see if it's interesting. So I call it dream coding. I've done a bit of dream coding here. Here's some example of defining some algebraic structures. This is not looking very different at all from records or structure types in Lean or Agda or ROC or any other type theoretic system. So far, so good. We've already got this sorted. But the first thing that I want to change is I want to make it so that I can seamlessly pass from a parameterized structure to a bundled structure and vice versa. So for example, I should be able to consider, you could call it like the quotient of the monoid theory by identifying the carrier with the natural numbers. And this would be another theory, but then I would have the elaborator could automatically insert the coercions that go from one of these specialized monoids to a fully bundled monoid. And by the way, if I the interpretation I have in mind for the semantics in book HoTT is literally just removing the field from the record and doing a substitution. So this type is actually going to be small. So I don't have a size problem here. So that's going to be pretty cool. Um, with this approach, it becomes really easy to talk about multiple structures that have the same carrier set. So for example, I can set up the assumptions of the Ekman-Hilton theorem here without any further ado. So I think there's something compelling there, and having a general machinery for this rather than needing to build it up very laboriously, I think is actually important. And credit where credit is due, the REND experimental proof assistant for a cubical-like version of HoTT actually has this feature. So that's really cool. Um, so now I want to deviate a bit from ML modules and RND records and so on, and say that I'm going to make it so that these theory declarations are generative in the sense of ML modules, but not in the sense of ML signatures for people who know what that means. So what I mean by generative is that the name actually is going to matter. There's an ice cream truck going by. I don't know if you can hear the little song it's playing, but in any case. The name is going to matter. And the reason I want to do this is I actually want to hang further definitions on that name. So here, I'm going to just say extend the semigroup theory with this operation called square, and it's just going to take an element and multiply it by itself. Just an example. This would be really difficult to achieve if the names didn't matter, that is, if a theory were defined just by its components, because again, I would have to use higher order unification in order to find out whether or not the square operation would be available on some instance of the semigroup theory. Whereas when I have the name, I don't need to use any unification at all. I can just say, oh, this is a semigroup? Okay, let me call the square method on that. And the interesting thing about this is not only that it's available on any semigroup, it's actually available on any monoid, and it's even available on nat monoid, which is any monoid structure on the natural numbers. And this is all going to be automatic. And this can be resolved without any kind of unification at all. It's literally just looking things up in the dictionary and only by names. So I think that's pretty interesting. This is stolen from Isabelle. That's how Isabelle locales work. And so they have whole libraries where you take a basic algebraic theory and then you extend it with all these operations. And so you have the theory of a group, and then group theory is all the operations that are applied to these groups. And then if you have a group somewhere else, you can use all those theorems by applying them to the group that you have. So the mode of use that I have in mind is, well, we set up the assumptions of the Ekman-Hilton theorem here. It's just an example. We set up the assumptions. Well, now we can extend it by the theorem. And if you specialize the Ekman-Hilton theory in the sense of using this slash thing, you quotient the theory by saying, okay, it has to be these two monoids. Then you can actually get the Ekman-Hilton theorem for those monoids. So the basic mode of use is you set up a theory whose fields are the assumption of the complicated result, then you have the result as an extension, definitional extension of the theory. So these I call them extensible named telescopes. They're named because the names matter, and they're extensible because I can attach definitional extensions to them from anywhere. And I think it's a lightweight alternative to type classes. It doesn't do everything that a type class does. But it does a lot of the things that a type class does. And I think experience with Isabelle's locales and the libraries of algebra that they've been able to construct in there shows that it's viable. We don't avoid needing unification at all. You still need it for implicit arguments. But maybe we don't need it as much for setting up algebraic hierarchies. So I think that's an interesting point in the design space that, as far as dependent type theory is concerned, remains unexplored. Let me talk about diamond problems too. There's a great paper, can't remember who authored it, but it's called Table Type Class Resolution, written by some people who work on Lean. And they came up with a great solution to the complexity blowup that occurs when searching a type class graph that has many diamonds in it. And the solution is some kind of very cool and advanced kind of memoization of the search. But one thing that one might not realize when reading that paper is that when they refer to the diamond problem, they mean only the complexity aspect, not the coherence aspect. So it's actually undefined how the coercions get resolved in the context of a diamond in Lean. This approach, based on Isabelle, solves the type class problem by enforcing coherence. Of course, that can be a bit of a violent thing to do, but there's a great idea from a paper called Modular Type Classes by Bob Harper, Manuel Chakravarty, and um, I think Derek Dreyer, but I'm sorry if I'm getting it wrong. And in that paper, they had the idea that you could add link edges to the graph locally. So you could have coherence, but without having to decide in advance what the graph looks like. So I think we could use something like that. And by the way, you can even have cycles in the graph. This actually works in Isabelle. So if something interesting is happening here. Okay, that's what I'm going to say about algebraic hierarchies. I think it's an interesting approach, and I think that it might work. I think that it might be usable. Um, Now I want to talk about something else that I didn't mention in my abstract. Inductive types they're always sort of the elephant in the room with figuring out how to define a type theory. Usually we punt on them in one of two ways. One way of punting on inductive types is to just have case trees and recursion, and maybe we don't have a termination checker yet, but maybe we hope to add one, or we do add one like they did in Agda. Okay, that's one way of doing it. Another way of punting is to just not have pattern matching at all and just emit eliminators, and you program with those. And neither of these is completely satisfactory for me. But luckily, there is some prior art that has not really been taken up by anyone fully, which we can use. So here's my theses on inductive types. The first thing is that, and I'll say a lot more about this in a moment. I want to follow Epigram. This is a proof assistant created by Conor McBride and his team, many ideas coming from James McKenna and others, in which they provided a pattern matching notation not just for the standard eliminator of a given inductive type, but actually for anything that's shaped like an eliminator, anything whose type looks like it has a motive and methods and a target. So that's interesting. And yeah, we can use the ideas of Jesper Cox and his co-authors on definitional. Sorry, what was it called? Eliminating dependent pattern matching without K. So the ideas in that paper can be applied to adapt the epigram idea to homotopy type theory. Just to reiterate, people say eliminators are important because we want to make sure that what we're doing is foundationally okay, and the eliminator is the mathematical side of things. All right. So that's one reason to eliminate pattern matching. But another reason to do so is because we can also apply the pattern matching notation to things other than the standard eliminator for a data type. So that's the really interesting thing. That's the power that no one has taken up since Epigram. And I'm going to talk about that. Termination checkers don't need you. Even Agda's relatively conservative termination checker has been constantly causing soundness bugs. And again, I'm not trying to pick on Agda. It's like an amazing project with very few resources that many people have many different agendas for. But we can also learn from that experience. And I think that these termination checkers, fancy or not, are kind of a dangerous idea. So, the thing is, you have a little bit of a termination checker that is doing something that goes just a little bit beyond standard structural recursion, but is still sound. And then someone says, oh, but why can't it eat my definition? My definition looks reasonable too. And then you try to hack it to make it work. And then the system becomes something that you can't understand. So, when I was a kid, they read us a book called If You Give a Mouse a Cookie, He Asks for a Glass of Milk. And this is, I think, what happens with these termination checkers. You just can't give the cookie in the first place. And the other thing too is that we can support higher inductive types natively because there's general schemas for generating or synthesizing the eliminators from reasonable signatures. There's a great paper of Ambush Kaposi and Andres Kovacs that shows how to do this. So we can deploy that too. Um, Here's the important usability issue. When you program with eliminators, you don't want to see the eliminator in the goal. This is like a huge nightmare if you see that thing. So hard design constraint from day one is that the user never sees an eliminator unless they wrote it themselves. So we can make it work. So why haven't we just been doing this for the last 20 years? Well, there's a few reasons. The first reason is writability. Eliminators are difficult to write program directly with, but as I mentioned, this is actually a solved problem. Conor McBride showed how to turn a pattern matching notation into eliminators. So there's no problem there. We can just use that. Readability. If the kernel uses eliminators, so if you have interpreted your pattern matching notation into eliminators, the kernel is using the eliminators, then it's going to show them to you, and this is a nightmare. You see this horrible term, you don't know what to do with it. It's too big, it can't even fit on your screen. Well, this is also a solved problem. There's a great paper called The View from the Left by Conor McBride and James McKenna. So they use an interesting trick, which I'll mention many times today, but I won't get to explain, called labeled types. And this actually can ensure that the user never sees an eliminator, even if they're programming with eliminators, standard eliminators, non-standard eliminators, doesn't make a difference. So this is a very powerful idea that not many people learned about. In fact, only yesterday did I realize quite how powerful it was after a chat with Conor. Um, Here's another one. Code written using eliminators is less efficient than general recursive algorithms. Well, this one's actually a little dubious because it really depends on what algorithm you're talking about and how the eliminator is being used. But I will just point out that even if there is a case, and I'm sure there's plenty of cases, no doubt, where it would be more efficient to write the general recursive algorithm without the eliminator at all, the labeled type trick actually also solves this problem. You can recover the naive general recursive definition that you intended to write um, uh, from the one using eliminators, so long as you keep the information about the intended program throughout the process. So this is another thing that can be achieved using labeled types, and you can see how to do it by reading Edwin Brady's PhD thesis. Finally, expressivity. Okay, maybe you do have some code that is like it's a reasonable, you believe it terminates, you're even certain it terminates, and you just want to write that code. And I say no, you can't write that code, I'm sorry. But what you can do is you can encode the idea of that code and its general recursion pattern into something that uses eliminators using the labeled types trick, and then a compiler can actually extract the code that you wanted to write in the first place for execution. So the expressivity problem is also a bit of a myth. We can solve that too using these ideas. So the current art. Lean, they compile the pattern matching to eliminators. The dependent pattern matching is a little bit rough around the edges, but the system is actually working pretty well, and it's getting better every day thanks to the investment of the Lean team and the FRO. So that's definitely promising and a good state of affairs. Rock has a very interesting package called Equations by Mathieu Sozeau. And they implement a bit more of the McBride and McKenna vision than Lean does. It's also a little bit rough around the edges, but it's really, really, really cool. I encourage you to try it out. And there was an original version many years ago, but there's Equations Reloaded. There's a paper some years ago. This one is much better than the original, so it's really worth checking out. It's very interesting. Well, one thing that both have in common is that they use accessibility predicates in order to interpret structural recursion, where you want to call yourself on a structural subterm, not just on the most immediate subterm, as would be justified by the direct eliminator. There's a little bit of a mess in Lean. They're making their accessibility predicates proof irrelevant, which destroys subject reduction. I'll say a little bit more about this soon. So let me come back to Epigram though. I mentioned that they have this general elimination of pattern matching for arbitrary eliminators, not just the standard one. So that's pretty cool. And I'll show you some applications in homotopy type theory and univalent foundations of where we can actually apply this to get really, really nice proofs that would be good for our libraries and for teaching and so on. Um, the other thing, this is even lesser known. Epigram, as far as I can tell, didn't use accessibility predicates. How is that possible? Well, they had a different method. They called it memo structures, inspired by an idea of Jimenez, and I'll say more about that soon. But there's an actual interesting operational insight here about how to design strong induction principles for type theory. So let's just see how these non-standard eliminators work in Epigram. So Conor gave this example in a position paper many years ago. So you're trying to write the projection function from a length index vector. I'm sorry about the length index vector. I know that we're tired of seeing those, but it's really all we have in this community. So you're trying to say, so you have the projection function, but now you want one that where you don't know if the index is within the bound. And you want to define that, and then you just want to return an optional result. You want it to return the right thing if it was in the bound and otherwise not. So a really easy way to do this would just be to run through the vector and convert it to a list and forget about the problem entirely. That would work. But it's a bit absurd to walk through the whole vector. That's n steps if you are just trying to project the first element of a long vector. So that seems like a waste of time. So Conor had this example, maybe a little bit of a contrived example, but it illustrates the problem and the solution. So, okay, we can project out a number from a finite, from an element of one of these standard finite sets. And so then he defines a non-standard eliminator, which basically says, okay, now you have a two-place motive and about two pairs of natural numbers. And in one case, it suffices to consider the case that it is within the bound. And then in the other case, if it's not within the bound, well, then it is the bound plus something. And so you just consider those two cases. So it's a without loss of generality kind of thing. And so you prove this thing. Okay, prove it, do it later, doesn't matter, because what we're going to do, we're going to use it. So we're trying to produce this optional projector thing. And so here's our current state. So now we're going to call the check bound custom eliminator. So I'm not eliminating using the usual eliminator. I'm actually calling the check bound eliminator on n and m. And now what it does is it gives me two pattern cases. One case for being in the bound and another case for being outside the bound. And so I know what to do in both cases. So that's done. You can simulate this in Agda using with abstraction and where clauses. But one, I think it's good to be direct. And two, this approach is going to give us very good display of goals. You won't see a bunch of messy stuff involving the custom eliminator in the goal ever, and that's a guarantee. Here's an example from HoTT. So we have set quotients. So they have an eliminator, a standard eliminator here. And so, okay, you need to eliminate into a set, fine. And then, okay, you need to send the points somewhere, and then you need to make sure you respect the relation. Okay. There's also an eliminator that you can do if you happen to know the motive is a predicate rather than a family. And this one is simpler to use because you don't have to do the second case. So if I were trying to show, for example, that the quotient map for quotients is surjective, it might be nice to use the second eliminator because this is an existential quantifier that tells me I'm doing a proposition. So I'll use that. Now I have just one case. Looks like pattern matching, but it's with a custom eliminator. Just one case. And then I can just return the value it's going to get there. So that's really useful. I mentioned something about the unfolding behavior. So this is what it would elaborate to in the kernel. But we can arrange that the user will never, ever see this term. They'll only see quotient map is surj u, if u is a stuck term. But if u is a constructor, if it's a point constructor, then we actually, this will disappear and it will unravel just to that case. So here we get the usability of Agda's pattern matching, which doesn't unravel the eliminator, but we get it for arbitrary eliminator-shaped things. So that's a huge usability improvement that I'm really excited about. Works for anything that looks like an eliminator. So that's a lesson that Conor tried to teach us a couple decades ago, and well, we didn't listen. Sorry, Conor. So here's some more interesting derived eliminators for HoTT. Function extensionality. You can think of that as an induction principle for based homotopies. That's interesting. Univalence. This is an induction principle for based equivalences. This will work for any univalent reflexive graph. We'll always get a derived eliminator that that will allow us to do something that looks like the J rule, but for some custom thing. So here's an example of a lemma from the HoTT book, Corollary 2.2.4. It's a naturality lemma. Right, so you can prove this in the usual way, but homotopy induction. Okay, now we have just one pattern case, we have the reflexivity case, and we do REFL, and we're done. It's not that different from the usual proof, but I think it's pretty nice. Here's another kind of contrived example. This is not how I would personally prove the associativity of composition of equivalences, but it's really cool that you can. So I'm going to do equivalence induction on F. Now my case is just the identity map. Equivalence induction on G, equivalence induction on H. It's all the identity map. Well, now everything is definitional and we're done. Okay, so I think that's pretty fun. And I think that this would be really good for teaching students the principles of univalent foundations. We also, okay, higher inductive types. What do we do? I think this will work too, actually. I think we can just have pattern cases for, AppD of the function on the path constructor. And, it's not going to compute definitionally, but that's okay. Nothing about the elimination of pattern matching notation needs anything to compute. And in fact, because in HoTT many of us will postulate induction principles for, maybe you want to work in a setting where you don't assume that we have pushouts, but then you want to assume that there is this particular pushout or something like that. Now you can use the pattern notation to work with those. So I think that this has a lot of potential to be useful in HoTT, maybe more useful in HoTT than it ever was for standard type theory. So I want to come back to accessibility predicates. So both lean and the ROC equations, they do well-founded recursion using the accessibility predicate, and that looks like this. The accessibility predicate for a two-place pseudo relation. It's a predicate on the carrier type A, and basically an element is accessible if every element that is strictly lower than it is accessible. It's the least thing close under that. So what you do is you come up with a relation on each data type, and this can be done automatically. That's what these systems do. And so for natural numbers, it's going to be the strictly less than relationship. And then you prove that every element of the natural numbers is accessible. And that can be done automatically. And so then when you define a structurally recursive function out of the natural numbers, first, the induction hypothesis gets generalized to have a proof of accessibility. And then you define the function by recursion on the proof, or by induction, I should say, on the proof of accessibility. And then the actual function itself is just achieved by applying that to the standard proof of accessibility for the given element. So this works totally fine. Lean uses it, and it's completely fine, at least in principle. When you make a recursive call, you just also pass in a proof that the thing is structurally smaller, and these get inserted by the elaborator, so that's okay. There's a subtlety, though. The elaborated function, it has to call the eliminator for the accessibility predicate on its accessibility argument. So the computation is stuck when the argument is, unless the argument is a constructor. And that makes sense, because otherwise you would just keep unfolding and unfolding and unfolding, and that wouldn't be good. The problem is that in Lean, they made the accessibility predicates proof of relevant. And this is immediately going to lead to undecidability because under proof of relevance, if any such H could be derived, then that a given witness is equal to that H. And therefore, that would mean that it would have to unravel. It would have to unroll the loop. So that's really dangerous because it's not possible to find out decidedly whether or not any such proof exists. So this manifests in the fact that definitional equality isn't transitive in Lean. Oops. Um, okay, a lot of gnashing of teeth. We can debate over whether this matters, but I always hear the old joke, Doctor, it hurts when I make accessibility predicate proof relevant. Well, stop making it proof irrelevant. Okay, that's the solution. So I want to, okay, accessibility predicates are fine, but you have to do them right. They are proof relevant, even if they are H-props. Okay, I want to compare this to an alternative approach that Conor McBride introduced, building on Jimenez's memo structure idea. It's a transformer of families, or modes of induction. The idea is that instead of generalizing the induction hypothesis to have a proof of accessibility, you instead generalize the induction hypothesis to just have all the possible recursive calls that you might make preloaded. So it's called memo because it's memoizing all the recursive calls. So the memo structure for a given inductive type can always be defined automatically. For natural numbers, it's simple. You just walk down the number and add an element of the motive at that number for each one. And then you generalize the function. So when you want to define a function by structural recursion, you use this generalization gadget. So if you're trying to make a function out of natural numbers, it suffices to make a function out of natural numbers where you have the recursive calls all preloaded. So that's what they did in Epigram. So let's compare the two approaches. First of all, they're equivalent. Why are they equivalent? Well, if you think about it really hard, you'll see it's because mapping out of a colimit is a limit. Okay. The reason is that you look at what the induction hypotheses will be for the recursive calls involving the accessibility predicate. Thing is, though, that limits work better than colimits in type theory. Interesting. Okay. Here's the operational insight. The sense in which limits work better than colimits in type theory is that when you're matching on or doing induction on the accessibility witness, you have to force it. So that makes, in the computer scientists will say it's strict in that argument. On the other hand, when you have the memo structure, you don't force anything. You just project, so it's lazy in that argument. So this is equivalent to accessibility predicates, but it is a bit more friendly for the type theory because you have stronger eta laws that hold. Because this big product of memoized recursive calls, it's a product. It has an eta law. The accessibility type will never have an eta law if we want to remain decidable. So that's a good thing. The other good thing is that if you combine this with the labeled type trick, which I didn't really explain how it works, but if you combine it, readability of the goals is ensured, and you'll never ever see the accessibility predicate. Okay, I have only a few more minutes. I know I'm going over. I'm sorry. I just have one last little thing to say. Okay. Something that I never took seriously in the past, and my work suffered greatly for it. I always built proof assistance in batch mode. What batch mode means is it's something that takes a file or a bunch of files and it runs my type checker, my parser, everything on there, and then it says, it didn't work, or it's okay, or here's the subgoals. It's better to think about the implementation of the proof assistant as a long-running process that the user interacts with through some kind of a protocol. There's prior art for this, of course. Going back to New Perl in the 1980s, it was basically a Smalltalk object database. Not Smalltalk, but it was like Smalltalk. It's amazing. Rock and Narya, they both have interaction servers. that can be wired up to Proof General. And Lean has a language server that provides IDE style features to lots of editors, including Visual Studio Code, which is, I think, what most users are using. Um, and this approach seems to be shared by many modern industrial programming languages where there's a lot of money that can be poured into making it work well. But one of the side effects of that money being poured into it is that we can take advantage of some of the things that people have built and use them in our own projects. Um, so, at first I thought, oh, I don't want to do that because I'm a purist. The kernel of my proof assistant, that's where the real work is happening. So I'll work on the kernel, and then at some point I'll throw a parser against the wall, and someone will figure out how to make it eat a file, and that'll be that. This was wrong. The thing about if we focus on the language server or the interaction model reified in software, um, this means that we can think really carefully about how users are going to interact with it from the start. And because I want to use this thing for teaching, this is actually really important. You and I, we can, use the system that is not very user friendly, and we can get over all the warts and rough edges, but students don't tolerate it. They don't tolerate it. They just stop doing it. Um, we can have good editor plugins, semantic highlighting. You don't need to write like a separate thing for Emacs or Vim or whatever. It will just work automatically, and the highlighting will be based on the semantics of the code. So kind of like how Agda works, except live while you're editing and works for all major editors. Um, you can have incremental elaboration, which is important if you have large libraries of mathematics. So this is something that works really well in Lean these days, and it's definitely something that I would like to have in my own systems. It works pretty well in Agda too, because Agda knows how to cache the results of elaborating a file. I want to be clear about that. But we can do it at a finer granularity, even at the level of keystrokes. That we can find the smallest scope to which it's possible to incrementalize, and we can do that. And then the other thing is that if you start with a batch mode system and then you try to make it incremental and interactive, this is extremely difficult. It's like pulling out your own teeth. So if we start with a design that will work for the interactive system from the start, I think that maybe this is a good idea. So anyway, I'm not criticizing anyone else. I'm criticizing myself because I've always done this wrong, and I'm finally getting it through my thick skull that I should do it the other way. So yeah, sorry, but old dog, new trick. Okay, so times have changed. Just because I'm talking about language servers in Lean doesn't mean we have to copy everything that they're doing. We can make some changes. I don't like how Lean reports an error when I'm in the middle of typing. I don't like how Lean has the goals disappear because I happen to be typing a solution to the goal and I haven't finished. We can solve that problem, and so can Lean. Anyone can solve that problem. So if you have a complaint about how Lean works, okay, let's talk about it and we'll fix it. We'll fix it for us, and then maybe they'll adopt the solution too. Um, I think that there's a lot of opportunity here to think really carefully about how this is going to work for both proof engineers and especially for students. So I'm really excited about doing that, and also about hearing from other people who are using HotUF to teach. So just to summarize, I'm getting to the end. I'm building a new proof assistant. It's going to take me a long time. I need help. I'm not going to use an experimental type theory. I want to have good algebraic hierarchies that work well enough for the rest of us, not for people who know how to implement a unifier. I want to have derived eliminators, and I want to use this to do really cool, exciting, delightful stuff in univalent foundations. I want to have fine-grained control over how things unfold. I don't want to see eliminators in my goals. I want things to be readable. And I want to have a rich editor experience from the start. It's a big project, and again, I'm going to need some help. Before I hand it over for questions, there's one more thing. I do have a prototype of some of this stuff. My prototype focuses on not on the eliminators, but rather on the theories and the locale stuff. And I'm not going to show you much of it, but I'm just going to very briefly try to just show you that it exists. So I'm going to quit the screen share, but I'll be still here. Let me try to do this. Let's see here. Uh, okay, I think you can see it. So the concrete syntax is terrible, I know, but I have some experiments here with implementing Isabelle style locales for dependent type theory. And you can see some of these examples where I'm able to splice in an existing theory and extend it by some new fields. And I'm able to do this in a way that allows me to build flexible hierarchies where, for example, I can talk about homomorphisms of semigroups, and I can define homomorphisms of monoids uh, using what I've already done for semigroups. And on the right-hand side, this hellish display is showing what all this stuff unravels to. So you can see that it does unravel to the structure you intended. Um, so just scrolling down, you can also extend you can extend existing locales or theories with new operations that are defined as definitional extensions. So I will just say my prototype is actually implemented in Lean. I'm using Lean not as a proof assistant, but instead as an alternative to OCaml or Haskell. So that's pretty fun. I don't know if I'll keep using Lean for this, but it has been a lot of fun. It's a great programming language. Anyway, I'm going to stop there. I'm going to put my slides back up in case there's questions. And yep, I'll hand it back to Carlo.
Great. Well, thank you very much, John Apple, for your thought-provoking and impassioned talk. So let's all visually applaud. And then, since there are a lot of people here, maybe it's best if you click the raise your hand button if you have a question, rather than just everybody trying to talk at once. We did get one question during the talk in the chat, which maybe I'll start with while people think about what they want to ask. So when you were talking about epigram, somebody asked, is being shaped like an eliminator, is that an intentional property, or what do you mean by that?
Yeah, that's a good question. Yeah, it's a syntactic property. I mean, it's syntactic up to definitional equality, of course. But the shape is you have something that is uh, looks like a motive, meaning it's pi XYZ blah 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 type. Then you have something that looks like methods for the cases and induction hypotheses. And again, this is something that we can recognize. All eliminators have the same pattern. That's why it's possible to generate eliminators from data type declarations. And then you have something that looks like the target of the elimination, which is the term of the data type that you're looking at and all of its indices. So this Epigram had a routine that would look at the type of some user supplied function and say, aha, okay, this thing looks like an eliminator, and I'm going to turn my crank on it.
Great. I guess Andy Pitts.
Oh, yeah, thank you very much. Hi, thanks, John.
Hi,
Very
Andy.
stimulating talk. Could you just make a comment or two about metaprogramming?
Mhm.
What I mean is it an important issue for you or an unimportant issue? Seems to me that Lean does it pretty well
Yeah,
compared with the other
yeah.
major candidates.
Yeah, it's a good question. To be honest with you, I'm not certain how important it is yet. I think if we were going to do it, we'd try and do, roughly what Lean does. Lean's metaprogramming works really well, and it's nice that the metaprogram is also written in Lean, or a dialect of Lean. So I think that's pretty cool. I do have a feeling, however, that if you squint your eyes using these custom eliminators, they look a lot like tactics. They look like backward chaining tactics that are doing left inversion on the context. So That's interesting. And maybe it will happen that many uses of tactics and meta programs would become examples of eliminators. Obviously, not everything will be. And you still want to do something like hook up a SAT solver or something. So I'm not going to have that as a priority for the first version, especially because I want a teaching friendly language. But I do think it's, potentially important, and we should learn from what they did in Lean.
Okay, I think Steve Audi is next.
Okay, thanks. Thank you, John. That was very inspiring. I agree with a lot of what you said, especially in the beginning about the usefulness of having another proof assistant, especially in the age of Lean, as you said in your abstract. I just wanted to put in a plug for our project here at CMU and with some other people online, Sina and Mario, some other people, to do a hot module inside of Lean. You might have heard about the Hot Lean project. I'll put a link in the chat where we're using Lean, and inside of Lean, we're building a hot proof assistant, which has a kind of under the hood compilation down to at present the groupoid model. And then it will return a kind of mathlib. The idea is you can use a synthetic language of bookhot, but it will be a synthetic proof in, say, groupoids. Later on, it could be in infinity groupoids or cubical or simplicial sets or something like that. But it will then compile out to mathlib, to classical mathematics. So that seems to hit at least some of the bases that you were asking for in the beginning. So I just wanted to mention that project. It's been going for 6 months or a year or something, and we're making some progress on that. And you might see some talks about it. I think there was one at Types. There's one coming up at some of the meetings. Wojtek is one of the people involved. So I just wanted to mention that. We can talk about it more in Cambridge when I see you there in a couple of months.
Great. Thanks, Steve. I look forward to hearing more.
Yeah.
Okay, I think Dan Christensen is next.
Hey, thanks, John. That was really interesting. I have two questions about what you are intending to include in your proof assistant. The first is whether you would have a tactic language. I'll pause and let you answer that
okay.
before I go on.
Yeah. So at the beginning, I don't intend to have a tactic language. I want to explore using these custom eliminators to cover many of the things that I usually do with tactics, which, honestly, when I'm using tactics, I'm usually doing revert, generalize, induction, P, and I have another way to do that. But for doing things like solvers and things like that, yeah, we'd need a tactic language, but it's not an initial priority for me.
Okay, I mean, related to that, I would say that, tactics do basically do these generalized eliminators currently. You say
Exactly, yeah.
apply this lemma, and it tells you to handle the cases that you need to do. So, second question is about type classes. So you talked about the difficulties in using them to organize an algebraic hierarchy. That's the case where the type classes are giving data, and data can be ambiguous, and so there are challenges with doing it that way. But there's many cases where a type class database stores propositional facts that are tedious to have to look up and remember the names for, and in particular, there can be long chains of implications. And these are very valuable in the HoTT library. You apply a lemma, and several of the goals are just solved for you through the type class search. So do you plan to include that kind of facility?
Yeah, I mean, it's an interesting point. I mean, one example would be for, if even like being a proposition is, that's a useful type class.
Yes,
and
that's
that's
very
closed under many
common, yeah.
constructions. So that's, definitely something to think about. on the other hand, if you look at how, say, something like the Agda UniMath library, and I think that the Rock UniMath library as well is organized, they tend to pack things like propositions and use defined constructions on propositions. So they'll take the product of a family of propositions rather than taking trying to prove that the product of the types is a proposition separately. Now, I know that can't do everything because sometimes you need to know that something is a proposition that you didn't know about in advance. So there's definitely still a place for some kind of resolution, and maybe type classes are the solution to that. But I'm interested in seeing how far we can get. And I'm encouraged by the fact that the people working on UniMath have managed to do so much with so little.
Okay, great. Thank you.
Okay, Mevin?
Hi, John.
Hi.
This is a really cool talk. I think I share a lot of your concerns or desires. So I'm really looking forward to being able to play with this proof assistant. So the question I had is around another pet peeve of Conor, one might say, which is that they have this thing about like turning up with what is it, algebra? No, what is it? Algebra to whatever fight. So
Oh, yeah, I know what you mean, yeah.
the point being that like our definitional equality is still extremely poor and could be made so much more strong. Things like, I don't know, the equational theory of rings could be just part of the definitional equalities, or another maybe less big thing, but like I've been working with coercions recently and having like transitivity or identity of like, or like functionality equations for free, things like that are not really things that are covered by the usual beta or eta laws of standard type theory. And I was wondering whether you had any thoughts in that direction, like this was something that you were interested in having in some way, or whether this was not really part of your grand vision.
Yeah, that stuff is definitely really interesting, and there's a lot of applications of, say having like definitional functor laws or monad laws and things like that. My perspective is that in the world of univalent foundations, like a definitional ring, might not really be exactly the same thing as a ring. There's some sense in which they are related. If you're talking about rings in the usual sense of having a set as a carrier, but there can be data in those proofs. So I'm a little, from the point of view of foundational orthodoxy, I'm a little worried about having some of these strictifications in the system. So I would say that would be a great example of something that maybe people could explore in a proof assistant that is more foundationally ambitious than what I'm planning to build.
All right, thanks.
Right. I suppose that kind of thing may also jeopardize the higher order unification that you want so badly, right?
Yeah, I'm a little worried about that too. Like it could be okay, but I don't know. It's a little frightening. Yeah.
Okay, Naeem?
Yes. Hi, John.
Hi.
You mentioned, if I understood you correctly, that no existing proof assistant implements the pattern fragment of higher order unification.
Yeah.
Did you mean that in the sense that, for example, something like Agda implements more than that, and so it's not as predictable as you wanted to, or did you
Well,
mean something
Agda
else?
has eta laws for the singleton for the unit type, and as far as I'm aware, so that means that the pattern fragment for the Agda type theory is maybe not the same as what the pattern fragment would be for, say, pure type system or something like that from the old days. And correct me if I'm wrong, but as far as I'm aware, Agda's unifier does not correctly handle the eta laws for singletons. So I think there's actually a ticket open about that, and it's a really subtle and difficult issue to solve. But I do believe that Andres Kovac, who may be in the room, I'm not sure, I believe that he knows how to solve the problem, although maybe there's some doubt as to whether it's worthwhile. But for me, as a matter of the design of these things, what is king for me is predictability and reliability. And so that means that if I'm going to include a unifier at all, it needs to have a well-defined fragment for which it's complete, and that fragment needs to be tailored to the features of the type theory. So it's very important from my point of view, so that we avoid strange errors or things that should work but they don't work.
Thanks.
Yeah, Jesper, feel free to unmute if you want to say anything, but Jesper says, I once tried to make pattern unification in Agda handle eta for unit properly, but sadly it was way too slow.
Yeah.
I suppose I will ask a question. So being an old man who used to batch mode interaction, I worry, I get nervous about the interaction mode first, in that it introduces possible path dependence, not in the usual hot sense, but of the state on like maybe the editor says that my file works with no goals, and then I close it, and then tomorrow I come and open the exact same file, and there's some problem. You know what I mean?
What would be an example of how that could happen?
Well, if since you're not reprocessing the file every time, maybe there's some sequence of events that get streamed to the through the interaction mode, where there's something out of sync between, the kind of streaming of events that get sent to the checker and like the file, the text file on your disk.
Yeah.
You know what I mean? Yeah.
Yeah, I mean, if that happens, it's a bug in the implementation of either the language client or the language server.
Right.
So yeah, I do agree there's a potential for those bugs, and I've seen them now that you mention it.
Yes. Yeah.
But bugs can be fixed. We can do it.
Sure. Yeah, that's fair. It's just a new class of bug, I suppose, that
Yeah, it's
doesn't
definitely a new,
exist
it's a new class of bug. But I will just maybe say that similar things can happen when your proof assistant is emitting like object files and things like that, and you can get some weird situation if you're not careful. So it's new in the sense that like the granularity of the cache it has the potential to become very fine, which
Right.
is likely to expose flaws in the implementation. But where I'm starting at a whole file granularity, and because it's very difficult to incrementalize things on like a definition by definition basis, although some systems do, like Rust's analyzer, I think, does. But I'm starting from something that is easier to do correctly, and then if it becomes worthwhile to incrementalize further, for example, if things are turning out to be actually really slow, then we can put in the time and effort to make that work.
Right. Right. And yeah, I think you're right. It's a question of granularity, that the finer the granularity, the more subtle and annoying the bugs will be.
Yeah.
But maybe it's only a new problem to those of us living in the past, though. So Matthew Weaver, go ahead.
Hey, so I am curious if you've thought at all about this being a appropriate setting, or potentially inappropriate, also to do software verification in the setting of homotopy type theory. So like if you have plans for an extractor not also being based on book hot, are there issues with univalent computing or what have you? So yeah.
Yeah, thanks for asking that question. It is not a priority for me to have this thing be usable as a programming language. I think it's important to have dependently typed programming languages, and maybe this one will become one, but there's a lot of interesting options in that space right now. And I'm more looking to tackle directly the problems of formalizing mathematics, especially structural mathematics. I think that there can be a lot of intersections and points of learning between the two goals, but I think that may be something that our community needs right now. is someone to focus on a system that isn't meant to be all things to everyone.
Makes sense. Thank you.
Yeah, sure.
All right, Owen, go ahead.
Although this, yeah, so you say you don't want this to be a system for programming. Even within just the framework of doing mathematics, I think that there's a good amount of programming, and there's also a good amount of desire for embedded languages that share a similar approach to the sort of, oh, we're going to extract general purpose code. Steve Audi mentioned like embedding HoTT into Lean. I could imagine that there are situations where you want to embed some sort of synthetic language into here and have it extracted out to, as you say, or orthodox mathematics. Have you thought about this, or do you have plans for how to handle this?
Yeah, maybe I'll have something, more interesting to say, a few years from now after we've learned from Steve and his collaborators' project for having a synthetic language in Lean that extracts into the groupoid model. My inclination is that, yeah, this is a worthwhile and a good problem, but there's a lot of research needed to figure out how to do it right. And I'm really glad that there's people who are exploring that. Wojtek Nawrocki over there is one of the people working with Steve on this, I believe, and I think he's doing his PhD on how to achieve some of these kind of translations in a way that will allow you to both access the synthetic side and the analytic side. So all that stuff is really great, but I would say I don't think we know how to do it right now, or at least not how to do it in a way that I would want to, tell people like this is definitely the way to do it from now on. Whereas what I'm starting to find is that both on the side of the type theory itself and on the side of the design of a proof assistant, we do have good answers that we can actually really endorse to the world for a more restricted feature set.
Yeah. Any last question? We're almost at the end of the half hours. Okay, well, if not, let's all just thank the speaker again. There are a lot of clapping emojis flying. So
Well, thanks everyone for coming. I really appreciate it.